Imagine, if you can, a state beyond imagining. Not empty space, for space itself did not yet exist. Not time, for time had no beginning. There was no before in the way we understand it, only an infinitesimal point of unimaginable density and temperature, a singularity that contained all the energy and matter of the universe yet to be. This is the conceptual starting point of our cosmic story, the moment known as the Big Bang. It wasn't an explosion in space, but rather an explosion of space, an instantaneous and rapid expansion that set the stage for everything that followed. Our journey begins approximately 13.8 billion years ago. In the first fleeting fractions of a second, an interval so minuscule it defies human comprehension, the universe underwent a period of exponential growth known as cosmic inflation. This hypothesis, crucial for explaining several observed features of the universe, posits that in an unbelievably short span, perhaps from 10 to 36 to 10 to 32 seconds after the Big Bang, the universe expanded by a factor of at least 1026, stretching from a subatomic size to macroscopic proportions. This rapid stretching smoothed out any initial irregularities, making the universe remarkably uniform on large scales, and flattened its geometry, explaining why space appears flat to us today. Without inflation, the universe would likely be a chaotic, lumpy, and highly curved place, vastly different from what we observe. Immediately following inflation, the universe was an incredibly hot, dense, and energetic primordial soup. Temperatures were so extreme, exceeding 1027 Kelvin, that matter as we know it could not exist. Instead, energy reigned supreme, giving rise to a sea of fundamental particles and antiparticles continually popping into and out of existence. This was the realm where the four fundamental forces of nature, gravity, the strong nuclear force, the weak nuclear force, and electromagnetism, were still unified or in the process of separating. In the earliest moments, perhaps all four forces were a single superforce. As the universe expanded and cooled ever so slightly, gravity was the first to freeze out, becoming distinct. This separation of forces is a cornerstone of modern physics, guiding the interactions of all matter and energy. As the universe continued to expand and cool, albeit still at mind-boggling temperatures, it entered the quark-gluon plasma epoch. From about 1012 to 10 to 6 seconds after the Big Bang, the temperature dropped sufficiently for the strong nuclear force to become dominant. This allowed quarks, the fundamental building blocks of protons and neutrons, to bind together, forming the first stable composite particles, protons and neutrons. For every particle, an antiparticle also existed, and they would annihilate each other upon contact, releasing immense energy. Crucially, for reasons still not fully understood, there was a tiny asymmetry, a slight excess of matter over antimatter. This minuscule imbalance, perhaps 1 part in a billion, is why matter exists today. If the balance had been perfect, all matter and antimatter would have annihilated, leaving a universe composed solely of photons. Over the next few minutes, as the universe continued its relentless expansion and cooling, temperatures dropped to around 109 Kelvin. This was the era of Big Bang nucleosynthesis, BBN, a critical period that determined the initial elemental composition of the universe. Protons and neutrons, now stable, began to fuse together under the intense heat and pressure. The simplest, atomic nuclei were formed, primarily deuterium, a heavy isotope of hydrogen, helium-3, and helium-4. Trace amounts of lithium-7 were also produced. Heavier elements like carbon or oxygen could not form during BBN because the universe expanded and cooled too rapidly for these more complex nuclear reactions to occur. The conditions necessary for forging heavier elements would only arise much later within the hearts of the first stars. The precise ratios of these light elements predicted by BBN theory remarkably match the observed abundances in the oldest, most pristine parts of the universe, providing powerful evidence for the Big Bang model. For the next approximately 380,000 years, the universe remained a hot, opaque plasma. Though nuclei had formed, the temperature was still too high for electrons to bind to them. Free electrons scattered photons, particles of light, constantly, preventing light from traveling far without being absorbed or re-emitted. Imagine being inside a dense fog, unable to see anything clearly. The universe was filled with this cosmic fog of charged particles. This era culminated in a monumental event known as recombination, or sometimes decoupling. As the universe expanded further, its temperature finally dropped to about 3,000 Kelvin, approximately 2,127 degrees Celsius, or 4,140 degrees Fahrenheit. At this critical temperature, the energy of the photons was no longer sufficient to keep the electrons from being captured by the atomic nuclei. Electrons combined with protons to form the first stable, neutral hydrogen atoms, and with helium nuclei to form neutral helium atoms. This seemingly simple event had profound consequences. With the electrons now bound within atoms, they could no longer freely scatter photons. The universe suddenly became transparent to light. The photons that had been bouncing around freely for hundreds of thousands of years were now able to stream, unimpeded across the cosmos. These ancient photons, stretched and cooled by the universe's expansion over billions of years, are what we observe today as the cosmic microwave background, CMB radiation. The CMB is perhaps the most compelling piece of evidence for the Big Bang theory. It's an almost perfectly uniform glow of microwave radiation coming from every direction in space, a faint echo of the universe's infancy. Its temperature today is a mere 2.725 Kelvin, just a few degrees above absolute zero. The tiny temperature fluctuations, variations of only a few parts per million, within the CMB are incredibly significant. These minute differences in temperature represent slightly denser or less dense regions in the early universe. These subtle seeds of density would, over billions of years, grow under the influence of gravity to form the vast structures we see today: galaxies, clusters of galaxies, and the cosmic web. The epoch of recombination marked the end of the universe's primordial plasma phase and the beginning of the cosmic dark ages. With the formation of neutral atoms, light could travel freely, but there were no stars or galaxies yet to produce visible light. The universe was a vast, dark expanse, filled almost entirely with hydrogen and helium gas, along with the mysterious dark matter and dark energy that would come to dominate its evolution. This period, though seemingly uneventful, was crucial. Within this darkness, gravity began its slow, relentless work, drawing together the slightly denser regions of gas and dark matter, setting the stage for the birth of the first stars and galaxies, and illuminating the cosmos once more. The story of the universe was just beginning to unfold its grand narrative, moving from a state of pure energy to the formation of the basic building blocks of all matter, ready for the next monumental transformations. The universe, having just emerged from the epoch of recombination, entered a period known as the Cosmic Dark Ages. This wasn't a time of literal darkness in the sense of an absence of photons, as the cosmic microwave background, CMB radiation, still permeated everything. Rather, it was dark because there were no stars, galaxies, or other luminous objects to produce visible light. The universe was a vast, featureless expanse, filled predominantly with neutral hydrogen and helium gas, along with the enigmatic dark matter and dark energy. This period, lasting for hundreds of millions of years, might seem uneventful, but beneath its seemingly placid surface, the fundamental forces of the cosmos were diligently at work, laying the groundwork for the spectacular structures we observe. Today, the primary architect of change during the Dark Ages was gravity. The CMB, as discussed in Part 1, reveals tiny fluctuations in the density of matter in the early universe. These minuscule overdensities, regions where matter was ever so slightly more concentrated, acted as gravitational seeds. Over vast stretches of time, gravity relentlessly pulled more and more hydrogen and helium gas, along with the invisible but dominant dark matter, towards these denser pockets. Dark matter, which does not interact with light or normal matter except through gravity, played a crucial role here. It formed the invisible scaffolds, known as dark matter halos, within which ordinary baryonic matter, the stuff stars and galaxies are made of, could accumulate. Without the gravitational pull of dark matter, the expansion of the universe would have been too strong for ordinary matter to clump together efficiently enough to form structures. As these clumps of gas and dark matter grew denser and denser, the pressure and temperature within their cores began to rise. This slow, inexorable gravitational collapse was the prelude to the universe's re-illumination. The first objects to form were not full-fledged galaxies, but rather smaller proto-galactic structures within which the first stars would ignite. These were the population 3 stars, a hypothetical generation of stars composed almost entirely of hydrogen and helium, the only elements available in the early universe. Unlike later stars, which are enriched with heavier elements forged in previous stellar generations, population 3 stars were pristine. The formation of these first stars was a monumental event, marking the end of the cosmic dark ages. Because they lacked heavier elements, which act as coolants, allowing gas clouds to collapse more easily, population 3 stars are theorized to have been incredibly massive, hundreds, even thousands, of times the mass of our Sun. Such massive stars burn through their nuclear fuel at an astonishing rate, radiating immense amounts of energy. They were incredibly hot, bright, and short-lived, existing for only a few million years before exploding as powerful supernovae. These first supernovae were crucial for the chemical evolution of the universe. They scattered the first heavy elements, carbon, oxygen, iron, and many others, into the surrounding intergalactic medium, enriching the cosmic gas and paving the way for the formation of subsequent generations of stars and planets. The light from these first stars and the subsequent explosions of supernovae began a process called ionization. For hundreds of millions of years, the universe had been filled with neutral hydrogen atoms, which are opaque to ultraviolet, UV light. The intense UV radiation emitted by the hot, massive population 3 stars began to strip electrons from these neutral hydrogen atoms, turning them back into a plasma of free protons and electrons. This process started in localized bubbles around the first stars and quasars, which we'll discuss shortly, and gradually spread throughout the universe. By about 1 billion years after the Big Bang, the universe was largely reionized, becoming transparent to light once again, much like it was before recombination, but this time due to the presence of luminous objects. This ionization event is another critical piece of evidence supporting our understanding of cosmic evolution, with observational data from distant quasars confirming the universe's transition from a neutral to an ionized state. As the first stars formed and died, the larger dark matter halos continued to grow, attracting more gas and smaller stellar clumps. These growing structures were the precursors to the first galaxies. These early galaxies were likely smaller and more irregular than the grand spirals and ellipticals we see today. They were still actively forming stars, fueled by the abundant gas within their nascent gravitational wells. These early galaxies were also characterized by intense star formation, often referred to as starburst galaxies, as the universe was still rich in the raw materials for stellar birth. Within some of these early massive dark matter halos, another powerful phenomenon began to emerge: quasars. Quasars are incredibly luminous, active galactic nuclei, powered by supermassive black holes accreting vast amounts of gas and dust at the centers of young galaxies. The sheer brightness of quasars, often outshining their entire host galaxy, allowed astronomers to detect them at immense distances, providing a window into the early universe. The existence of supermassive black holes so early in cosmic history poses an intriguing puzzle for cosmologists, suggesting that these colossal objects must have formed remarkably quickly, perhaps from the direct collapse of massive gas clouds or from the mergers of smaller black holes. The powerful radiation from quasars also contributed significantly to the ionization of the universe. The formation of these first stars and galaxies marked the end of the cosmic dark ages and the beginning of the epoch of galaxy formation. The universe was no longer a uniform dark expanse. It was becoming a dynamic, luminous arena where gravity continued to sculpt matter into increasingly complex structures. These early galaxies were not isolated islands. They were part of an emerging cosmic web, a vast network of filaments, sheets, and voids. Dark matter provided the gravitational scaffolding for this web, with galaxies forming along the filaments and at the nodes where filaments intersected. The voids, vast empty regions, represented areas where matter was initially less dense and gravity had less material to work with. The universe was still relatively small and dense compared to today, meaning galaxies were much closer together. This proximity led to frequent galaxy mergers and interactions. These mergers were crucial drivers of galactic evolution, triggering bursts of star formation, reshaping galactic morphologies, and feeding the supermassive black holes at their centers. The chaotic dance of merging galaxies was a defining feature of the early universe, laying the foundation for the larger, more mature galaxies we observe in the present day. The story of the universe's awakening is one of transformation from simplicity to complexity. From a uniform, neutral gas, gravity sculpted the first dense pockets, igniting the first stars that brought light and forged the first heavy elements. These stars, in turn, Ryanized the universe, clearing the cosmic fog. As these stellar nurseries evolved, they coalesced into the first galaxies, which then began to merge and grow, forming the intricate cosmic web. This period, spanning from a few 100 million years to about 1 billion years after the Big Bang, was a time of rapid and violent creation, setting the stage for the more familiar universe of mature galaxies and solar systems. The journey from primordial soup to a universe teeming with light and structure was well underway, but many more billions of years of evolution lay ahead. Having witnessed the universe's re-illumination by the first massive stars and the nascent formation of proto-galaxies, our cosmic narrative now moves into an era of grander scale and increasing complexity. This period, spanning from roughly 1 billion to several billion years after the Big Bang, is characterized by the continued evolution of galaxies, their maturation from irregular stellar nurseries into the majestic structures we observe today, and the relentless cycle of star formation that would eventually forge the very elements necessary for planets and life. The cosmic web, once a faint scaffolding of dark matter, now became visibly populated with luminous galactic nodes, engaged in a perpetual dance of growth and interaction. The early galaxies, as described in Part 2, were often smaller, more irregular, and highly active, undergoing intense bursts of star formation. However, over billions of years, these nascent structures began a process of galactic evolution driven primarily by gravity and the continuous flow of gas. Smaller galaxies merged to form larger ones, a process that continues even today. These galaxy mergers are not gentle unions. They are often violent gravitational encounters that rip apart existing structures, trigger new waves of star formation as gas clouds collide and compress, and reshape galactic morphologies. The chaotic dance of merging galaxies gradually transformed the irregular, clumpy structures of the early universe into the more familiar, organized forms we see in the mature cosmos. The majestic spiral galaxies with their distinct arms, the smooth elliptical galaxies, and the more chaotic irregular galaxies. Spiral galaxies, like our own Milky Way, are characterized by a flattened disk containing spiral arms, a central bulge, and a surrounding halo. Star formation is most active within the spiral arms, where gas and dust are compressed. Elliptical galaxies, on the other hand, are typically older, redder, and have less active star formation, often thought to be the end product of multiple major galaxy mergers that have consumed most of their gas. Irregular galaxies, as their name suggests, lack a distinct regular shape and are often the result of gravitational interactions or ongoing mergers. The type of galaxy a region of the universe hosts is often a clue to its past, with ellipticals more common in dense galaxy clusters where mergers are frequent. At the heart of many, if not all, large galaxies lies a supermassive black hole. These colossal objects, millions to billions of times the mass of our Sun, play a crucial role in galactic evolution. In the early universe, as gas and dust funneled towards the centers of young galaxies, these black holes began to accrete matter at prodigious rates, becoming the incredibly luminous quasars that illuminated the distant cosmos. The energy released during this accretion process can be so immense that it pushes gas away from the galactic center, a phenomenon known as feedback. This feedback can regulate star formation within the galaxy, sometimes quenching it by expelling the very gas needed to form new stars. The intricate relationship between a galaxy's central black hole and its star formation history is a key area of modern astrophysical research. Within these evolving galaxies, the cycle of star formation continued unabated, but with a crucial difference from the population 3 stars of the cosmic dark ages. The supernovae explosions of those first massive stars had enriched the intergalactic medium with the first heavy elements: carbon, oxygen, nitrogen, iron, silicon, and many others. This cosmic dust and heavier elements were now incorporated into the gas clouds from which subsequent generations of stars would form. These are the population 2 stars, metal-poor, older stars found in galactic halos and globular clusters, and later, the population 1 stars, metal-rich, younger stars like our Sun, found in galactic disks. The process of star formation begins within vast, cold, and dense molecular clouds, regions of gas and dust within galaxies. Under the influence of gravity, denser pockets within these clouds begin to collapse. As a pocket collapses, it spins faster due to conservation of angular momentum and flattens into a rotating protoplanetary disk, or protostellar disk, with a central protostar. The temperature and pressure at the core of the protostar continue to rise until they reach a critical point, approximately 10 million Kelvin. At this temperature, nuclear fusion ignites. Hydrogen atoms fuse to form helium, releasing enormous amounts of energy. At this moment, a new star is born, entering the main sequence phase of its life, where it will spend the majority of its existence, steadily burning hydrogen in its core. The life cycle of a star is determined primarily by its initial mass. Massive stars, hundreds of times the sun's mass, burn hot and bright, but live short, spectacular lives, ending in colossal supernova explosions. These explosions are not only breathtaking cosmic events, but also the primary cosmic factories for even heavier elements, scattering them across the galaxy to be incorporated into future generations of stars and planets. Less massive stars, like our Sun, live for billions of years, eventually expanding into red giants, shedding their outer layers to form beautiful planetary nebulae, and finally collapsing into dense, Earth-sized white dwarfs. Even smaller stars, red dwarfs, can live for trillions of years, slowly dimming. The remnants of massive stars can be incredibly dense neutron stars or the ultimate gravitational traps, stellar mass black holes. Crucially, it is within the hearts of stars, through the process of stellar nucleosynthesis, that all the elements heavier than lithium are forged. From the carbon in our bodies to the iron in our blood, the oxygen we breathe, and the silicon in our planet's crust, every atom, except for hydrogen, helium, and a tiny bit of lithium from the Big Bang, was once cooked inside a star. The universe is literally made of stardust, and the continuous birth and death of stars are essential for enriching the cosmos with the raw materials for complexity. As stars formed within the protoplanetary disks, the remaining gas and dust did not go to waste. Within these swirling disks, particles began to collide and stick together, a process known as accretion. tiny dust grains clumped into pebbles, pebbles into rocks, and rocks into larger bodies called planetesimals. These planetesimals continued to collide and merge, slowly growing into the planets we know. The inner, hotter regions of the disk tended to form rocky planets, like Earth and Mars, while the outer, colder regions allowed for the accumulation of more volatile compounds, leading to the formation of gas giants, like Jupiter and Saturn, and ice giants, like Uranus and Neptune. The formation of our own galaxy, the Milky Way, is a story woven into this larger cosmic tapestry. It is believed to have formed through a series of mergers of smaller galaxies and gas clouds over billions of years. Its distinct spiral structure, with its central bar, bulge, disk, and halo, is the result of these evolutionary processes. Our Sun, a relatively young star, formed within one of the Milky Way's spiral arms about 4.6 billion years ago, surrounded by its own protoplanetary disk that would eventually coalesce into our solar system. Throughout this grand process of galactic evolution and star formation, the enigmatic components of the universe, dark matter and dark energy, continued to play their dominant roles. Dark matter, invisible and mysterious, provides the gravitational glue that holds galaxies and galaxy clusters together, forming the backbone of the cosmic web. Without its pervasive gravitational influence, galaxies would simply fly apart due to their rapid rotation. Dark energy, on the other hand, began to exert its influence more strongly as the universe expanded and became less dense. While gravity worked to pull matter together, dark energy began to accelerate the expansion of the universe, pushing galaxies further apart. This accelerating expansion, discovered in the late 1990s, is a profound mystery that continues to baffle cosmologists, shaping the ultimate fate of the cosmos. This period, from the first billion years onward, saw the universe transform from a relatively uniform expanse of gas and nascent structures into a vibrant, luminous cosmos teeming with billions of galaxies, each a sprawling metropolis of stars, gas, and dust. Within these galaxies, stars were born, lived, and died, enriching the universe with the elements of life. And around these stars, planets began to coalesce from the leftover cosmic dust, setting the stage for the emergence of complex systems, including our very own solar system, a small but significant corner of this vast and ancient universe. The conditions for life were slowly but surely being assembled. From the swirling cosmic dust within the arms of the nascent Milky Way galaxy, our story now narrows its focus to a singular, remarkable event, the birth of our own solar system. This is a tale of gravitational collapse, accretion, and the serendipitous alignment of conditions that would ultimately lead to the emergence of life. Approximately 4.6 billion years ago, a vast, cold cloud of interstellar gas and dust, known as the solar nebula, began to collapse under its own gravity. This nebula was not pristine. It was enriched with heavy elements, the stardust, forged in the hearts of previous generations of stars, and scattered by their explosive deaths. This enrichment was crucial, providing the raw materials for rocky planets, water, and the complex chemistry of life. As the nebula collapsed, it began to spin faster and flatten into a rotating disk, much like a cosmic pizza. At the center, the vast majority of the mass accumulated, increasing in density and temperature. This central clump became our proto-sun. As the pressure and temperature in its core soared, eventually reaching the critical threshold of about 10 million Kelvin, nuclear fusion ignited. Hydrogen atoms fused into helium, releasing immense energy, and a star was born. Our sun entered its main sequence phase, a stable period of hydrogen burning that would last for billions of years, providing the steady energy source essential for life on Earth. Meanwhile, in the surrounding protoplanetary disk, the remaining gas and dust continued their intricate dance. Particles collided and stuck together through a process called accretion. Tiny dust grains grew into pebbles, pebbles into rocks, and rocks into larger bodies known as planetesimals. These planetesimals, ranging from kilometers to hundreds of kilometers in size, continued to collide and merge. In the hotter inner regions of the disk, volatile compounds like water and methane were vaporized, leaving behind only rocky and metallic materials. This led to the formation of the inner rocky planets, Mercury, Venus, Earth, and Mars. Further, out in the colder reaches of the disk, volatile compounds could condense, allowing for the accumulation of vast amounts of hydrogen and helium gas around icy cores, leading to the formation of the gas giants, Jupiter and Saturn. Beyond them, the even colder temperatures allowed for the formation of ice giants, Uranus and Neptune, composed largely of heavier elements like water, ammonia, and methane ices. Our home planet, Earth, formed through this violent process of accretion. In its earliest phase, known as the Hadean Eon, approximately 4.6 to 4.0 billion years ago, Earth was a molten, hellish landscape. Intense volcanic activity spewed lava across its surface, and the planet was subjected to a relentless barrage of asteroids and comets, the remnants of the solar system's formation. This period of heavy bombardment, particularly the late heavy bombardment, around 4.1 to 3.8 billion years ago, sculpted the surfaces of the inner planets and our moon. It was during this turbulent Hadean Eon, around 4.5 billion years ago, that a colossal collision between the early Earth and a Mars-sized protoplanet, often called Theia, is theorized to have occurred. The immense debris ejected from this impact coalesced in orbit to form our large, stabilizing moon, a celestial companion that would later play a crucial role in regulating Earth's tilt and tides. As the bombardment subsided, and Earth gradually cooled, a critical transformation began: the formation of its oceans and atmosphere. Water vapor, outgassed from the planet's interior through volcanic activity and delivered by comets and icy asteroids, condensed as the surface temperature dropped below the boiling point. Torrential rains fell for millions of years, filling the lowest basins and forming the primordial oceans. This early atmosphere was vastly different from today's, rich in volcanic gases like water vapor, carbon dioxide, nitrogen, and sulfur compounds, but largely devoid of free oxygen. With the presence of liquid water, a stable surface, and a protective atmosphere, the conditions for life slowly began to assemble. The early Earth was a dynamic chemical laboratory. Energy was abundant, supplied by volcanic activity, lightning, and intense ultraviolet radiation from the young sun, before the formation of an ozone layer. Essential elements like carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur were present in various compounds. Scientists hypothesized that life did not arise in one single warm little pond, but rather through a series of complex chemical reactions occurring in diverse environments. The scientific quest to understand the abiogenesis, the origin of life, from non-living matter is one of the most profound challenges in science. Several leading hypotheses attempt to explain this transition. One prominent idea is the RNA world hypothesis, which suggests that RNA, not DNA, was the primary genetic material in early life. RNA can both store genetic information and catalyze chemical reactions, like enzymes, making it a versatile molecule capable of self-replication. Another compelling theory points to hydrothermal vents on the ocean floor as potential cradles of life. These deep-sea vents release superheated, mineral-rich water, creating chemical gradients and energy sources that could have driven the complex reactions necessary for forming organic molecules and eventually self-replicating systems. The protective environment of the deep ocean would also shield early life from harmful UV radiation. Regardless of the precise location or mechanism, the first life forms were incredibly simple. Prokaryotes, single-celled organisms lacking a nucleus, or other membrane-bound organelles. These ancient microorganisms, likely anaerobic, living without oxygen, thrived in the early oceans. Evidence of their existence comes from ancient fossilized structures called stromatolites, layered rock formations, built by communities of microorganisms, some dating back as far as 3.5 billion years ago. These early life forms began to subtly alter their environment, consuming available chemicals and releasing waste products. A pivotal moment in Earth's history, driven by early life, was the Great Oxidation Event, GOE, also known as the oxygen catastrophe, which occurred roughly 2.4 billion years ago. Certain types of prokaryotes, particularly cyanobacteria, often called blue-green algae, evolved the ability to perform photosynthesis. This revolutionary process used sunlight, water, and carbon dioxide to produce energy, releasing oxygen as a byproduct. Initially, this oxygen reacted with abundant iron in the oceans, forming rust-colored sediments known as banded iron formations. Once all the available iron was rusted, free oxygen began to accumulate in the atmosphere. This was a slow process, taking hundreds of millions of years, but its impact was transformative. For many existing anaerobic life forms, oxygen was a deadly poison, leading to a mass extinction event. However, it also opened the door for the evolution of new life forms that could tolerate and eventually utilize oxygen for more efficient energy production. Throughout this early period, plate tectonics played a crucial role in shaping Earth's surface and influencing the evolution of life. The movement of massive tectonic plates recycled Earth's crust, created continents, formed mountain ranges, and drove volcanic activity. This geological dynamism created diverse habitats, influenced ocean currents and climate patterns, and provided the raw materials and energy sources necessary for life's continued development. The interplay between geological forces and biological evolution was, and remains, a fundamental characteristic of our planet. For an astonishingly long period, over 2 billion years, life on Earth remained exclusively single-celled and microscopic. This vast stretch of time, often overlooked in the grand narrative, was a period of immense microbial diversification and adaptation, laying the biochemical and genetic groundwork for all the complex life that would follow. The stage was set, the planet was alive, and the conditions were slowly ripening for the next great leap in complexity, the emergence of multicellularity and the explosion of diverse life forms that would populate the oceans and eventually the land. The journey from cosmic dust to a living world was complete, but the story of life's intricate unfolding had only just begun. Having established a living planet, the stage was set for life to embark on its most spectacular evolutionary journey. For over 2 billion years, Earth was dominated by microscopic single-celled organisms, but around 1.5 billion years ago, a revolutionary leap occurred, the emergence of multicellularity. Simple cells began to cooperate, forming colonies, which eventually led to organisms composed of many specialized cells working in concert. This innovation was the prerequisite for all complex life forms we see today. The pace of evolution dramatically accelerated with the Cambrian explosion, roughly 541 million years ago. In a geologically brief period, the oceans witnessed an astonishing diversification of complex animal life. Most major animal phyla, including the ancestors of vertebrates, appeared during this time, each experimenting with new body plans, sensory organs, and predatory-prey relationships. This era laid the foundation for the intricate food webs that define ecosystems. Following this oceanic boom, life began its audacious conquest of land. Around 470 million years ago, plants, having evolved adaptations to prevent desiccation and absorb nutrients from soil, began to colonize the barren continents. Their presence fundamentally altered the terrestrial environment, creating new habitats and paving the way for animals. The first land animals, likely arthropods, emerged around 420 million years ago, followed by vertebrates. Amphibians crawled from the water, then reptiles evolved greater independence from aquatic environments, leading to the age of the dinosaurs for over 160 million years. The end of the dinosaur era, around 66 million years ago, was marked by a catastrophic asteroid impact, one of Earth's 5 major mass extinction events. While devastating, these events also cleared ecological niches, allowing for the rapid diversification of surviving groups. In this case, it was the mammals who seized the opportunity. Evolving from small, nocturnal creatures, mammals diversified into an incredible array of forms, eventually leading to the primates. From these primate ancestors, a lineage emerged that would eventually lead to our species. Through millions of years of gradual change, marked by the evolution of bipedalism, increasing brain size, tool use, and complex social behaviors, hominins began their journey. This culminated in the appearance of Homo sapiens in Africa roughly 300,000 years ago, a species characterized by unprecedented cognitive abilities, symbolic thought, and an insatiable curiosity about the universe around us. Today, we stand at a unique juncture. Our species, a product of billions of years of cosmic and biological evolution, possesses the capacity to understand our origins and shape our future. The universe continues to evolve, galaxies drift apart, and stars are born and die. Life on Earth, a delicate and resilient phenomenon, continues its intricate dance of adaptation and change. The story of the universe is an ongoing narrative, and humanity, with its consciousness and ingenuity, is now a self-aware participant in its grand unfolding epic.